Okay, let's get started. We're going to talk about optimization or maximization and minimization. Okay, so you learn to take a derivative, and you know that what that process does is it gives you a formulaic way of expressing the slope of a nonlinear function. Now you have a way of expressing the slope of the nonlinear function. Well, there's certainly things you can say about slopes of complex nonlinear functions, but one of the ways in which you use that information is to determine the maximum or minimum of that complex nonlinear function. Often in science or in policy, you're trying to look for the value of x which either maximizes or minimizes the function that you care about. This assumes that there's a functional relationship, that is, changing x leads to a change in the f of x or in the function. So there is some underlying belief in causality. Some underlying reason to think that there's causality between x and f of x. Okay, it's not like the example in your primer where you might have two variables that are related, but they're not actually causally related. Okay, so if they are causally related, and you understand how the slope of that function works, you can use the nature of that slope to determine the value of x, or the value of the input variable, which will either maximize or minimize the function of interest. Okay? That maximization might be local or global. So here is a convex or concave function. Concave function is a concave function that attains a maximum at the point S. Well, what's special about that point S is that at that point S, the derivative of this function is equal to 0. Right? The slope of the function is equal to 0. Okay. A concave or a convex function? Convex, right? This is a convex function. And this convex function has the property that at the point R, it attains a minimum. At that point R, the slope of the function f of x, or the derivative f prime of x, is equal to 0. Okay? So in both these cases, here the function attains a maximum, here the function attains a minimum, the derivative of the function is equal to 0. Okay? It turns out, of course, that if you have a convex function and its derivative is equal to 0, then you're likely to be attaining a minimum. If you have a concave function and its derivative is equal to 0, or it's flat, the slope is flat, then you're at a maximum. So concave functions attain their maximums at points where the slope is equal to 0, and convex functions attain their minimums at the point where their slope is equal to 0. Yes, you had raised your hand.
Is this only assuming that there's only a single point?
Yeah, this is for a single point, but within the interval that I'm showing. It could be that this is a complex nonlinear function that goes like that. This function will still attain a local maximum here. It may not be a global maximum. There may be some other point where there's a global maximum. But nevertheless, this will be a local maximum. And generally, you'll care both about local and global maximums. So with the example of the carbon dioxide emissions, carbon dioxide concentrations I talked about, you are probably going to care about the shape of that function near its current value and not far away from it, even though some related phenomenon that you care about might attain a global maximum far away from the current value of greenhouse gas emissions. If this were a plateau, what you would see is that the tangent line would have a slope of 0 at many points. It can certainly be the case that fx attains a maximum at many points s, but they'll nevertheless be local maxima. Okay? So it doesn't have to be a single point. Okay, generally, okay. Okay, now, so a key piece of information you have is that to find the maximum or minimum of a nonlinear function, you know that a feature of that point is that the derivative is going to be equal to 0. So if you're faced with a higher order polynomial, let's say a complex nonlinear function or relatively complex nonlinear function, here I've drawn what it looks like, okay? But even without drawing what it looks like, I could take its derivative that you already know how to do. So that's going to be 15x to the 4 minus 60x squared. You could take that derivative, find the values of x for which that derivative is equal to 0, and then you know that at those values of x where the derivative is equal to 0, the function might be attaining a maximum, a minimum, or possibly a point of inflection such as this. This is neither a maximum nor a minimum. But what you do know is that if you find the derivative of this function, set it equal to 0 and find all the values of x for which the derivative of this function is equal to 0, all those values of x will comprehensively determine the critical points of this function. Critical points meaning maxima, minima, and points of inflection. Okay, and so you would, what you could do here is you could plot, once you find the derivative of this, did I tell you what that was? Yeah, so that is 15x to the 4. That's the derivative, 15x to the 4 minus 60x squared. Okay. I could look at this, and if by graphing this, I see that the function is really interesting between the points minus 2 and, well, it's, if I determine the behavior before minus 2, between minus 2 and 0, from 0 to 2, and then above 2, I'll have a good sense of how the function looks. And that's what I try to do here. So I say, what I want to know is what are the values of the derivative of this function before minus 2, at minus 2, between minus 2 and 0, between 0 and 2, and above 2. So I could choose these numbers, -3, -1, 1, and 3. Plug those numbers into the derivative, so it tells me what the slope of the original function will be at those points. So this is the derivative, and I evaluate this derivative at these 4 different values of x. If x is equal to -3, I plug -3 into that equation, I get 675. If x is equal to -1, I plug it into that, I get -45. If I plug 1 into that, I get -45, and then 675 again. So that tells me that when x is -3, the function is steeply upward sloping. Is that the case? Yes, it's going up steeply, right? And when x is 3, it's also steeply upward sloping. And that's what's happening here. And in between, it changes around. For example, at -1, it's downward sloping, and at 1, it's also downward sloping. And I know that at 0, it's flat. Okay? And I'm just doing that here. Okay, so here I'm plugging in the values -2 and 2. Since I know that those are, in addition to this point 0, which is a point of inflection, these are the other points where the derivative is equal to 0. By the way, the definition of a point of inflection also is the point at which concavity changes to convexity. Okay? What you're doing, the way actually, even without the graph, what you do is, see, when you solve for this, when you get the first derivative, you would solve for the zeros of this function. Okay? You want to know, because of the graph, it's easy for me to tell you that -2, 0, and +2 are the points where the slope is 0. But if you didn't have the graph, you would take this equation, set it equal to 0, and solve for the values of x where that was true. Now this happens to be a polynomial of degree 4, so it'd take you a long time to solve this by hand. I would not ask you to do this in an exam. But if you plug it into MATLAB, it'll turn it out in 2 minutes, 2 seconds.
And wouldn't that give you what you're looking for, though? Instead of 0?
It'll give you the values of x where this is equal to 0. So I would know that, and actually what it'll do is it'll give me these 3 values. Right. Okay? Yes?
No. It's just like when you
All I'm saying is that I would take, I computed this derivative. That's a slope. That's a function that gives me the slope of the original function. Okay, I know, so if I put in any x here, this expression will give me the slope of the original function for that value of x. Now, I want to know the values of x for which this expression is equal to 0. Okay, well, how do I get that? I simply set that expression equal to 0, and I solve. Oh, actually, I chose an easy example, so you don't need MATLAB to do this, right? You can tell, because this is a square of that, so that's a useful feature. So if I want to set this equal to 0, and then I solve for x. Okay, so that's going to be 15x4 is equal to 60x squared. Okay, I divide both sides by x squared. Okay, but when you divide, and this is something useful to keep in mind when you solve equations, I can eliminate x squared. I can eliminate x to the fourth from here by dividing both sides by x squared, but I have to keep in mind that there is one case when I'm not allowed to divide by x squared. And what case is that? That x is equal to 0, because our mathematics is unable to divide by 0. Okay, so I keep in mind that I have to examine the case that x is equal to 0, and then I divide both sides by x squared. So I get, and then I divide both sides by 15. Okay, so this reduces to a simple equation. So then the roots of this are just minus 2 plus 2, and then I have to look at the case where x is equal to 0. Okay, so I must have chosen that polynomial so that this could be done by hand. But generally, but this is a pathological example. Most examples won't be like this. Okay. Okay, so this you've already seen. If we have a concave function and it's a smooth function that attains a maximum at x star, then of course its derivative is equal to 0, and its second derivative at that point is less than or equal to 0. If it's strictly concave, then it'll be strictly negative. This was, if you go back to an earlier slide, recall that having the second derivative be negative was the definition of a concave function. Okay? So this is a concave function. If it's concave and its slope is flat, then it's attaining a maximum. If it's convex and its slope is flat, it's attaining a minimum. Okay? Okay. Okay, how's everyone doing? Okay, I actually have quite a lot of examples. So we may not get to the multivariate calculus today, but that's not unexpected. We will simply catch up on it in the next session, and we'll probably do a little less of the integration and so on. Remember, we got to spend most of the time on the simpler 20% of the topics.